Today's lecture is on volatility. Let me start by giving you an outline of today's lecture. First of all, given that we are concerned with risk management arises because something unexpected or something extreme may happen in the future. So one way or the other, we need to deal with the uncertain future, and because we are going to measure and manage risk, we have to assume model assumptions in order to do so. So one way to deal with that uncertain future that I will introduce today is to use returns that are normally distributed. We will see that it's a proxy, that it will work very well in many cases, and in some cases we need to do alternative things. One of these things I will discuss at the end of today's lecture. When we take the normal distribution to represent this uncertain future, then one of the crucial parameters in that normal distribution is the volatility. So I will formally introduce volatility today, give you definitions of it, and then look to ways in which volatility may be specified. One of the important elements is that volatility may change over time. When volatility is low, we are reasonably certain about what's going to happen. When volatility is high, then the uncertainty increases. In particular, we will focus on two updating schemes. The one is the exponentially weighted moving average updating scheme, and the other one is what will be referred to as the Garch 1-1 scheme. Once these two schemes have been discussed, I will use the Garch 1-1 volatility scheme to actually first estimate it and afterwards use it to forecast future volatilities. So that's a way to get an idea of how volatility will develop over time, so how uncertainty in the future will develop. In particular, volatility also is important when we look to the pricing of options. As we saw, the volatility is an element that goes into the Black-Scholes formula. Given that now we have a more specific idea of how volatility may be forecast over time, we can also use that to get an improved value for the volatility that goes as input into the Black-Scholes formula. So we will in particular see how these updating schemes for the volatility have an effect on option pricing, and then in the end also on option risk management. And then I'm talking about the Vega risk. And as you remember, Vega risk is concerned with changes in the volatility. As we will see there, it matters whether an option has a long-term or a short-term when we are going to assess the impact of instantaneous volatility change. At the end of today's lecture, I will look to the power law. What the power law does is that it says, well, if in particular you are interested in extreme events and the probability of extreme events, then we know that normal distribution very often doesn't work very well. So what the power law does, that gives you a way to extrapolate your data and then to look much further in the tail of your distribution to assess the probability of extreme values. So this is just one way. There will be other ways, but in particular it's an alternative to the normal distribution function if you believe that you are really now interested only in extreme events. So the volatility really is there as an element in how we are going to do a risk representation. In the previous lectures, we have been talking about risk sensitivities. We have been talking about duration, convexity, about delta, gamma, vega, and so on. Those are all sensitivities for what the impact is on the value of a bond or the value of an option if some of the underlying market variables changes. So what we will be starting to do today is to say, well, how actually could these market values change? So think about market variables such as interest rates or stock prices, exchange rates. So we have understood now how to measure the sensitivity of prices of financial securities if interest rates change or if the stock price changes. But we have not dealt yet to a large extent with, well, how can these interest rates or these stock prices change? So now we move to model the uncertainty in the future market variables. And to do so, we very simply assume, and that's an approximately reasonable assumption, we assume that future returns are normally distributed, at least approximately. Well, if we assume a normal distribution, and we will see there are a lot of very nice features with that, then the most important parameter in that normal distribution is the volatility. Because what the volatility does, it's a measure of dispersion, so it gives you a range. It sets the range for the possible future returns that may occur. And very formally, the volatility is denoted with sigma, and it's the standard deviation per unit of time. And as you will see, we can measure volatility on a daily basis, on a monthly basis, on an annual basis. Very often what we do, no matter what the basis is that we use to estimate the volatility, for example, as the standard deviation of past returns, that's one possibility. Then afterwards, what we do is that we annualize the volatility. That means if the volatility was measured on a daily frequency, then afterwards there's an updating formula to express it in annual terms. And same applies with monthly data. So if we estimate volatility as, for example, the standard deviation of historically monthly observations, then afterwards we annualize that volatility to express it in terms of annual deviations. That's simply a way to standardize the volatilities. So one more step. So we talk about the uncertain future, and in particular we are then talking about returns. So there's two types of returns that are important. First is return with continuously compounding. So here is a formula. It says RT plus 1. So that's the return at one moment in the future at time t plus 1. And the C says that it's a return with continuously compounding. And the way that you determine that is that you take the natural logarithm of the price of the security at time t plus 1, and you divide it by the price at time t, by pt. So as an alternative, a more familiar return, there is the discrete return. That's denoted with RT plus 1D. So D stands for discrete and T plus 1 stands for the moment that the return is observed at time T plus 1. So there you take the difference between the price at time T plus 1 and the price at time T, and you divide it by the price at time T. So for modeling purposes, what we will do is we will in particular stick with continuously compounded returns. So with these returns, it's much natural to assume that they are normally distributed, and also there are very nice features if afterwards we have to go and add up returns, something that we will have to do. Then if returns are determined with continuously compounding and we add them up, then if the individual returns are normal, then the sum of these returns are normal again, and that's a nice feature that we are going to use. For all practical purposes, if returns are not too high or not too low, so if we are not concerned with extreme events such as a return of minus 50% or plus 40%, then actually the discrete returns and the continuously compounded returns, if you calculate them, they are very close to each other. So suppose that you would be looking to daily returns, where the returns usually are not that extreme, then it doesn't matter so much whether you do the calculation of discrete returns or continuous returns, because the same number will almost come out. But from a mathematical, theoretical point of view, the continuously compounded returns have the better properties that we need afterwards when we are going to include normal distributions and so on. So we assume that this return, and here I dropped the C for continuously compounding because it should be clear by now that if I talk about returns, it's always about continuously compounded return unless stated otherwise. So I assume that future returns, because they are uncertain, that I can represent them with a normal distribution. And here it says, well, there will be a mean of mu and there will be a variance of sigma square. So if these returns are on a daily basis, then very often what happens is that the effect of the mean, the average drift that there will be in a daily return is so low, in particular if you compare it to the value of sigma square, which is much larger also on a daily basis, then the effect of the variance is so dominant compared to the effect of the mean that very often simply this mean return is set to zero. That simplifies a little bit life. But so if you find that inconvenient, you might as well simply still incorporate the mean. But so if you see people setting the mean equal to zero, it's for that reason. It's because of the dominance of the variance compared to the mean. So how does that uncertain future then evolve? Suppose I'm looking to a financial security which price at time zero is S0, I call it the price of a stock. Then at time zero, the price is still known, but then if we move forward, then the future becomes uncertain, and the future asset prices value are simply have unknown values. So we treat them as random variables. And then the way that we calculate or determine these future prices is always through the returns. And so here I mentioned that S1, which is then a random variable, it's the possible value of the return one period from now. Then we take the known asset value at time zero, S0, and we use continuously compounding to arrive at the price at time one. So that's the exponent to do the continuously compounding, and R1 is then the return if you move from time zero to time one. For S2, the same applies. So S2 is the unknown value of the stock price at time 2. To determine that, I take the stock price at time 1 and I multiply that with the exponent and then the return from time 1 to time 2, so that's R2. So what I could do then is I could use the upper formula for S1 and I could substitute it in this formula for S2. And then I get that S2 in fact is equal to the original price S0 times the exponent R1 times the exponent R2. And then there is a nice property if you multiply exponents. It's then simply you can add up the returns R1 plus R2 and put them within the exponents. So if you would generalize this formula to longer time periods, so I'm looking to the uncertain return or the uncertain price of a stock at time capital T, so in the future, T periods in the future, I take the known value of the stock today and I multiply it with the exponent and then the sum of all these 1 year or 1 period returns. So what it says is if I want to determine a future stock price, I simply look to the returns that will evolve over time. I add them up and then this aggregated return is put within the exponent to arrive at the price at time t. So all these future returns are unknown. So in fact, they are all random variables, all normally distributed. And so if efficient market hypothesis holds, and we assume that it does hold, then all these returns are also independent. That's important if we look to the statistical properties later of these returns. So this is a nice way to say, well, if I use returns to represent the uncertain future, then I do see how that then in fact has an effect on the uncertain value of financial assets in one period from now, but also in multiple periods from now. I mentioned in the introduction that the volatility is an important parameter in the normal distribution to represent this uncertain future. And what I said is, well, in fact, what it does, it sets the range of possible outcomes. And what I did in this graph here is that I simply looked to the normal distribution where the mean return is always 8%, but then I drew the graph for different volatilities. And then the blue line, which is in the middle, is the line if the volatility is set to 10%. So on the x-axis you see possible returns. So possible returns range from minus 60% and minus 40%, minus 20%, 0, 20, 40 and 60%. So returns to the right I like a lot, and returns to the left I do not like at all. So from a risk management perspective, at least what the graph does is it says, well, how good can things turn out, how well can things turn out, and how bad can things turn out. So if I look to this graph on the y-axis, it's the instantaneous probability. So really, if I have to look to the possibility of something happening, I need to look to the area under the graph. But what the graph shows me is also with this first line where the volatility is 10%, the range is somewhere between minus 20% and say plus 30%, because beyond that, the more extreme values almost have no probability mass under the graph. Then instead, if I look to the red line where the volatility is set to 15%, then suddenly you see that the probability mass is higher and still elevated. For example, when I look to returns of minus 30%, but also on the other side, plus 40%, you see that there is a larger probability that this could happen compared to the case where the volatility was only 10%. Well, let's look to the most extreme case where the volatility is set to 30%. That's the light blue line on the outside. So here you see that even extreme returns like minus 50% and minus 60%, they have probability mass. So then if the volatility is actually 30%, then we see that these very extreme returns could appear. So from a risk management perspective, volatility is important because it's an immediate measure about the range of possible outcomes, and it's an immediate measure of, say, how bad things could turn out. So it's important to take care of this parameter and to carefully model it, estimate it, and think about its evolvement over time. In this graph, I took actual monthly returns of the S&P 500 stock index. So this index is a representation of how the stock market in the US develops over time. And so from 1987 to 2019, you see that indeed there are periods where there are extreme positive or extreme negative returns, but there are also periods where the returns actually are much slower. So there are periods where there's a minus 24% in a particular month, or a minus 18%, minus 16%, but there are also periods where returns are plus 12%, plus 10%, and more quiet periods where the monthly return is within plus 4 and minus 4%. So we see that volatility may change over time. So I took the summary statistics of this data sample, and so first point of remark, the average monthly return on the stock on the S&P 500 index is 0.7%, and the standard deviation is 4.31%. So here you see the same thing that applies to daily return to some extent also applies to monthly returns. We see that the standard deviation, which is a measure for the volatility, is really dominant compared to the average value. So the average value has far less effect on risk management considerations than the standard deviation. So sometimes people simply ignore it and put it to 0 or leave it out. Sometimes they incorporate it, but the largest effect for deviations in the future, and that's what we are concerned with, will come from the standard deviation, which is 4.31% on a monthly basis. So the most extreme negative return in 1 month was minus 24.5%. The most positive return was 12.3%. And next, what I did is I took all these observations and I tried to calculate how often very extreme returns occurred. So I said, well, how often does an event occur on a monthly basis where the return is worse than -5 times the standard deviation? And -5 times the standard deviation is -22%. So I counted the number of events that the returns on a monthly basis in this data sample was more extreme than -22%. And it was in 0.2% of the cases. Same I did for -4 standard deviations. So that's a monthly return of -17%. So how often did it occur that returns were more extreme than -17%? Well, that turns out to be in 0.4% of the cases, and so on. So you see for -3 times the standard deviation, so returns more extreme than -13%, 0.6% of the cases. And on the other side, so I looked also, so how often returns were more than 1 standard deviation. So returns were more than 4% on a monthly basis, 16% of the cases. 2 standard deviations, so how often returns were more than 9% on a monthly basis, 2% of the cases, and so on. And the reason that I did this is to draw a comparison with the normal distribution, because the normal distribution, if I know the mean and the standard deviation, I could also take a lookup table and say, well, what would have been the probability implied by the normal distribution function if the average is 0.7% and the standard deviation is 4.31%. And then, so an important difference between what actually happens in practice and what the normal distribution function does as a proxy for return. So what you see is that the very extreme returns, so very far in the tail, the normal distribution function says, well, hey, that will almost not occur. So the probability is 0% for -5 standard deviation, it's 0% for -4 standard deviation, and only if I look to -3 standard deviation, so returns below -13%, then the normal distribution says, well, that's in 0.08% of the cases, whereas in reality it's in 0.61%. So the normal distribution function has far less extreme tails than empirically occurs. So what we say is that empirically the tails are fatter, so there are more observations in the tails than the normal distribution function represents. So there's an underestimation there if we look to the data. And the same applies for extreme positive events. So we see that 3 times the standard deviation and 4 times the standard deviation, the normal distribution function has more values there than empirically are observed. And then in the middle of the distribution, there are overlaps. So 10% versus 12%, 16% versus 20%. So it provides a similar shape, but it's not exactly the same. So what we do say is, well, the normal distribution function is approximately right, but not to the extreme. So how to use this normal distribution function? Suppose that we do know, one way or the other, that the expected return of a financial asset has a mean of 8%, denoted with mu is equal to 8%, and a standard deviation of 18%, that's the sigma here. So how does that help you to reflect future risk? Well, you could do that in 2 ways. First of all, you could say, well, given that I know these parameters, so the mean of 8% and the standard deviation of 18%, could I determine what the probability is of a negative return? The answer is yes. So I look to the probability that the return is smaller than 0%. So this return is a non-standardized normal distribution. So what I'm going to do, I'm going to transform it in a standardized normal distribution function. You do that by demeaning the variable and by dividing by the volatility. So that's happened next. So there's RT minus the mean, mu, divided by sigma. If I do that on the left-hand side of the variable, I also need to, of the equation, I also need to do it on the right-hand side. So it says 0% then minus 8% divided by 18%. And then this RT minus mu over sigma is a standardized normal random variable, which is denoted with the Z that you see there. And so the Z should be smaller than 0.44%. So if I need to determine that, I need to go to the cumulative normal distribution function for the standard normal distribution, which is denoted with the capital N, and I need to look up 0.44% in that lookup table. Alternatively, you could, for example, use the norms dist function in Excel. So if you do that, then looking up this value, then it says there is a probability of 33%. So that's a way to reflect future risk. So if I know the mean and the standard deviation of this random variable, I can determine the probability that the return is negative, and in this example, that return would be 33%. So that's important for an investor, because he may say, well, I find that very risky, so in 33% of the cases, I will get a negative return on this investment. Maybe I would like to change it to an investment which is less risky. Second way to work with these data is the other way around. You could also say, well, I want to look to extreme events, and I determine an extreme event as an event where there's only a very small probability that there will be events worse than this extreme event. And let's say for this case, as an example, we say an extreme event is an event where there's only a probability of 5% that the event will be even worse. So I'm going to calculate the negative return, which I denote with NR in the formula, that goes with such a low probability of occurrence. So it says here the probability that the return, which is the random variable, is smaller than this negative return should be 5%, because 5%, I say that's a low probability. I need to standardize again the non-standard normal distribution function. I do that by subtracting the mean mu and I divide by the sigma. If I do it on the left-hand side, I also need to do it on the right-hand side. So then it says negative return minus the mean divided by the sigma, and it should be equal to 5%. So then this RT minus mu over sigma now is a standardized normal distribution random variable, which is denoted with the Z. So it's the probability that Z is smaller than NR minus mu over sigma is 5%. I'm going to take the inverse of the normal distribution function. That's the same as looking up the critical value in the standard normal distribution function table that's associated with a probability of 5%. So then it says NR minus mu over sigma is equal to this normal inverse at 5%. Or if you rewrite it, that negative return that I'm looking for is equal to the mean of the return plus sigma of the return, the volatility of the return, times that critical value of the standard normal distribution function at 5%. So let's fill in the numbers. The mean is 8%, the standard deviation is 18%, and that critical value that goes with a 5% probability mass in the left tail is equal to minus 1.645. So if I do the calculation, then what comes out is that there is a negative return of minus 22%. So what it says is, well, if I want to be 95% certain about a return, then I know that, well, with 95% certainty, the return will be better than minus 22%. So there's only a 5% probability that the return, the future return, will be even worse than the minus 22%. So that's an idea to get. That's a way to get an idea about how extreme could returns turn out. So you could also calculate this at a value of 1%, for example. Then you even are more certain about the extremity of the return. And we will revisit this type of analysis afterwards in a later chapter where we will talk about value at risk. So now let's look to some properties of returns. So these returns, these continuously compounded returns, we assume them to be independent and for the moment also that they are equally distributed. If that is the case, then it's very easy to move from one frequency to another frequency. So suppose that we have determined return volatility on a daily frequency. So that means that we have taken historically observed returns and we have determined the standard deviation of that. Then afterwards, if we would like to understand what the return would be on a weekly basis or on an annual basis, we can simply transform that daily volatility. So in this case, the daily volatility is 1.5%. So if we move to other frequencies, then the natural assumption that we take is to say, well, a year has 252 working days. So if I want to move from a day volatility to an annualized volatility, then what I need to do is this annualized volatility, which I denote with sigma y, y for year, is then equal to the square root of 252 times the daily volatility. So that would imply an annualized volatility of 23.8%. So it says, well, if I look to volatility in the sample and I see that on a daily basis it's 1.5%, that's similar to if I would be looking to returns on an annual basis, then the uncertainty in the annual returns would be equal to a volatility of 23.8%. I could also go from a day to a week. Then we know that in a year there's 252 working days and there are 52 weeks in a year. So I take 252 divided by 52 to approximate the number of days in a week. And again, I need to take the square root to determine the transformation from day to week. And that gives me then 3.3% is the volatility on a weekly basis. So I mentioned it before, what we like to do is we like to express volatility on an annualized basis because that's where we have the best feeling for when volatilities are low or when they are high. So these numbers mean the most to us. But you can, in principle, work at any frequency. So another property. So there is a property that uncertainty in future returns increases with the square root of time. So I will move back now to a formula that we introduced a little bit earlier. That's where we said, well, if you look to the future stock price at time capital T, and we are today at time 0, then to arrive from time 0 to time T is you have to multiply with an aggregated return. So you have to add up all the returns in all the future periods. That's the sum of T is 1 to capital T of RT. And you have to take that to the exponent and multiply that with the S0. So what it says is that the aggregate return really is simply the sum of all the individual returns, and this aggregate return I denoted with capital RT. So now let's look to that return over time, this aggregated return. If I would take the variance of this RT, then that's the same of taking the variance of the sum of the 1 year returns. Well, the variance of a sum is the same as the sum of all the variances if the returns are independent, and we assume the returns to be independent. So that says then I can take the sum of time is 1 to capital T of the returns, the variance returns, the VRT. Because we also assume that returns are equally distributed, we say that all these returns, all these future returns have the same volatility, have the same variance. Volatility denoted with sigma and the variance denoted with sigma square. So the variance, the VRT, is nothing but sigma square. Well, now there is no index anymore with the sigma square. So that means that if I take the sum from T is 1 to capital T of sigma square, I'm simply adding up capital T times the variance. So that is then capital T times sigma square. Then if I want to go from variance to standard deviation, because standard deviation is my measure of uncertainty and time, then I need to take the square root of the variance. I need to take the square root of capital T times sigma square, which is the square root of time times the volatility. So what it says is, well, if I look to a 1 period return, then my volatility is equal to sigma. If I would look to a 2-year, 3-year, 4-year, 5-year period return, then I take the cumulative return of that. But the associated volatility is not the sum of the daily volatilities, but it's the square root of the time period times the volatility. So the uncertainty increases, but it increases not linearly, but less than linearly. It increases with the square root of time. And that's an attractive property because it says, well, then at least if returns, the expected returns, increase linearly and the uncertainty only increases with the square root of time, then then uncertainty is increasing at a lower rate, lower pace. So we have seen that volatility is an important variable. There are many different ways that people try to assess the value and the development of volatility. And so what I will do in the next couple of slides, I will look to some of them. Easiest case is the constant volatility assumption. So if you say, well, I'm looking to an uncertain future, but I believe that the uncertainty, the dispersion, the range of possible outcomes will not change over time, then you assume volatility to be constant. And if you want to have an appropriate proxy for what that volatility then would be, what you simply do is you take the standard deviation of historically observed returns, and that's also then the volatility, the constant volatility that you apply in your risk management assessments going forward. Second thing that you could do is you could use an implied volatility. How does that work? As you remember from the Black-Scholes formula, to determine the price of an option, you have to put in the volatility and other variables. What you also could do is you could say, well, I observe the price of the options and I'm going to see, well, what is the volatility that I have to put into the Black-Scholes formula to get to this observed option price. And that's in fact reverse engineering the volatility from the Black-Scholes price. So instead of having the volatility an input to the Black-Scholes price, we take it as an output from the Black-Scholes formula. And we call that the implied volatility. So what is the value of the volatility implied by option prices? And assuming that the Black-Scholes formula gives a good representation. There's also the VIX index, which is now for a couple of years available, which gives you such an implied volatility directly, and which is then a measure also of how uncertainty over time increases. Then there are two other cases that are quite common in practice, but also in the academic world. The first one is the exponentially weighted moving average, and the second is the generalized autoregressive conditional heteroscedasticity model. For the latter, Nobel Prizes were given. So what these two models do is they provide updating schemes, and they provide updating schemes because they said, well, volatility is not constant over time, but volatility may sometimes be higher and sometimes be lower. And it's important to know that because when volatility is lower, then there is less uncertainty. And when volatility is higher, there's more uncertainty. So we need to take that, that variation in volatility into account. So let's start with the implied volatility. So I do observe the price of an option. I can simply go to the newspaper and look what that value is. And what I do is I fill all the known values of an option into the Black-Scholes formula. And once I've done that, I'm going to look with a goal seeker. I'm going to look, well, what is the volatility that I should plug into the Black-Scholes formula to set the price of the Black-Scholes formula equal to the observed price of the option. And so here I did a simple example in Excel where the current stock price is 30 and the exercise price is also 30, risk-free rate 5%. the dividend yield is 0. Then the sigma, you see in yellow, it's the number that I need to determine. And the remaining time to maturity is 1 year. I calculate the D1 and the D2 as elements for the Black-Scholes formula. And I see the Black-Scholes price of 2.8 and I see the observed price of 2.8. And at the bottom you see the objective that I try to minimize, try to set equal to 0. Well, it's here something like 4 times 10 to the power minus 8. So that's almost 0. So what I did with the gold seeker, I said, well, change the yellow field, which then in the end turns out to be 17%, to set the Black-Scholes price equal to the observed price, to set the objective, which is the difference between the two squared, equal to 0. So what this means is that this call option that I use, which has a value of 2.8, implies a volatility of 17%, and which has then also said, well, this implied volatility says something about the uncertainty in the underlying stock return, because I believe that stock return then has a volatility of 17%, implied by options. So then now let's look to the weighting schemes. The first weighting scheme is the exponentially weighted moving average weighting scheme. Let me first introduce some notation. So here we assume that volatility is not constant over time, but volatility is changing over time. And then to represent the volatility at day t, I use as notation sigma t. So sigma for volatility and t for the moment in time. And next to that volatility, I also need to have an innovation, which says, well, what kind of news did there come into the market? And I use ut at time t, which is then an innovation, which I determine as the return that was realized minus the average return. So any deviation from the average return is an innovation. And if that deviation is high, then we say there is a lot of news. If that deviation is low, then we say, well, we are somewhat close to the average, so there is less news. And more news is then interpreted as more uncertainty. And then the third element that we use is a persistency parameter. In practice, this parameter is very often set to 0.94. It's denoted with lambda. And then the weighting scheme is as follows. So what we say is, well, we look to a volatility, a daily volatility that we want to determine at time n. So we take sigma n square, which is then the variance, of course, at time n. And we say, well, we believe that there is a relationship with the volatility at the previous day, sigma n minus 1 square. We multiply that with lambda. And there's also then the effect of news that is arising in the market. And this news, this innovation, is then the deviation that we saw at the previous time period, so the un minus 1. So this difference between the return and the average return. And also this difference, we need to square it. So what this says is that, well, if I want to determine the volatility today, then I attach most weight to the volatility as I calculated it yesterday. 94% is attached to that value. And 6% is then attached to the most recent innovation that occurred in the previous time period. So that's 6% of un minus 1 square. So this is an iterative relationship where every time you can do a volatility updating. To have a more theoretical say consideration of what actually happens is you could also rewrite this formula into a formula where, say, the sigmas disappear and there's only the innovations that appear. And then what the formula says is, well, the variance at time n, the sigma n square, is the weighted sum of all the past innovations squared. So the un minus I squared are multiplied with alpha I, and the alpha i's are the weights, and un I squared are the innovations as they took place in the past. So if I is 1, then it says the innovation at time n minus 1. If I is 2, it's the innovation at time n minus 2, and so on. And as I gets larger, you go further back in the past. You look to returns which occur further back in the past. So before we go and look into detail to this alpha I, there's a special case of this formula, and that's the case where the alpha I would be equal to 1 over m. If it's equal to 1 over m, then really what you say is, well, I assume that all the past innovations have equal weight, and then I'm back in the case of a simple standard deviation that I calculate on past observations. So what the exponentially weighted moving average relationship does is that it says, well, no, we want to give less weight to observations that occurred further in the past and more weight to innovations that occurred more recently. So this alpha I, if you look to it, it's really 1 minus lambda, and then the important part, the lambda to the power I minus 1. The larger I gets, the further I move into the future, and the larger I gets, the lower is the value of lambda to the power I minus 1. Because lambda is a number smaller than 1, so if I take the powers of that, the more powers I take, the smaller the outcome is. So in this case of the exponentially weighted moving average formula, the further I move into the past, the less I believe this past innovation is representative for the innovation that or for the uncertainty in the market that I look at today. I still give it weight, but the further away I give it less and less weight, which seems a natural thing to do. So if I apply this exponentially weighted moving average formula to daily historical S&P 500 returns, so in this case from somewhere 2005 to 2011, you do see that sometimes volatility is below 1%, sometimes it moves up to between 1.5% and 2%. We see that around the financial crisis there was a spike, then suddenly volatility goes up to 5%. A lot of news in the market, which then also is reflected in more uncertainty in the volatility. And then after the financial crisis, you see that it's going further down. 2010, it's around 1%, then a little bit later, again, there is some uncertainty, 2%, and so on. So we do see that if we believe that volatility is time varying, that the data suggests at least that there is indeed time variation, and that sometimes there are periods with low uncertainty and sometimes a period with high uncertainty. And very naturally, if we look to this graph, then indeed, when there is the financial crisis, there is a lot of uncertainty, and the exponentially weighted moving average model picks that up. So an important consideration to assume that volatility is not constant, but has time variation. Now let's move to the second updating scheme. In this updating scheme, same as with the exponentially weighted moving average, we look to shocks in the previous period, the UN minus 1 square, and we look to the volatility in the previous period, sigma n minus 1 square, but we also add to the formula an omega. And what the omega does is the omega assures that there is a long-term average variance that where the volatility in the long term is pulled back to. And that's not a property that the exponentially weighted moving average has. Very often what we do, and I will discuss that in a minute, is that we set the omega equal to 1 minus alpha minus beta times the long-term variance, VL, because then it's easier to estimate this model. So in this case, you have to estimate the omega, the alpha, and the beta from historical data. You could apply the maximum likelihood principle to that. It's important to impose restrictions, stationarity conditions, to make sure that the model does not explode if you're going to forecast with it. And also because it's a nonlinear optimization, if you're going to do the maximum likelihood optimization, it's good to scale the variables. So there are a lot of more technical aspects that you need to take account of if you want to estimate the values of this model. So I like very much myself the variance targeting method. In that case, what you do is that you say, well, I don't treat omega as a separate parameter, but I set it equal to 1 minus alpha minus beta times the long time variance. And this long time variance VL, you could simply determine it as the historical variance that you would observe. So I'm looking to all the observations that I have. I calculate the variance of all these observations, and that's my VL. And then if this value is known, then I could simply substitute it in the equation. And what I get is I get a model where sigma n square is considered in excess of VL. The V is on the right-hand side. And then the effect of a shock, so the UN n minus 1 squared, is considered in excess of the long-term variance. And the effect of the variance in the previous period, the sigma n minus 1 squared, is also considered in excess of the long-term variance. So it's a model where all variables are now considered in excess of the long-term variance. What it also does, and that's very practical when you go and estimate these models, because it's not trivial to estimate these models, it gives you 2 parameters to estimate, the alpha and the beta, instead of 3. And very often, if you try to estimate the model with the 3 variables, including the omega, it's far more difficult to say from an operational point of view, to find the optimal values. Whereas the statistical properties are that this omega should have this relationship with the long-term variance. So you might as well take care of that. And then in this case, there's only 2 parameters that remain to be estimated, so the alpha and the beta. If you're going to estimate them, so the VL is already known, you have determined that from the historical variance, so alpha and beta remaining. So there's the updating scheme. So if you're going to estimate it, you apply the maximum likelihood principle to do that. There are a couple of constraints that you need to give to the solver to make sure that that this nonlinear optimization function actually is not going to values that would not fit with this model. So what you should do is you should add restrictions to the optimization. The first restriction that you should add is the positivity constraints for the alpha and the beta. They both need to be greater than 0. And the second restriction that you need to add is a stationarity constraint, which says, well, the alpha plus the beta, if you add them up, that needs to be smaller than 1, because otherwise the model would afterwards explode if you try to forecast with it. So it becomes an explosive model, a non-stationary model, whereas if it's smaller than 1, it is stationary. So I've done that. So I've looked to the S&P 500 daily returns from July 18, 2005, August 13, 2010. So I applied that maximum likelihood principle, took care of the scaling, took care of the positivity constraints and the stationarity constraints. You could use a nonlinear optimization routine. Excel has one. I wouldn't say it's the best one, but there's other software packages who do have that. And once I've estimated these values, so then you see that the omega appears as 1 minus alpha minus beta times the long time variance. And then the alpha and the beta are 0.15 and 0.84 respectively. So the sum of these two is smaller than 1, so the model is stationary. And in terms of interpretation, the beta of 0.85 says, well, the volatility today is to a large extent related to the volatility yesterday, because there's a 0.85 weight on the volatility yesterday. And it has, and it's for 15% for 0.15 times the innovation that took care yesterday squared. So you see then the balance between, well, the historical volatility and the innovation that took place. So that means that there is persistency in volatility. So volatility is moving over time, but it is persistent, that it sticks to similar values as you move over time. And that's also what you see if you then plot the fit of the model from 2005 to 2011. So we see very similar to the exponentially weighted moving average model. We see that the volatility sometimes is low, around 1%, and then we see that it gets higher in the crisis period where it gets to 6%, and then it gets lower again when it goes to 2010. Please note that this is daily volatility, and when we look to the exponentially weighted moving average, we work with monthly volatility. That's why the numbers on the y-axis are also different. Well, now that I've estimated this model in sample, and I've looked at how volatility evolves over time, the question is if I can also use this volatility updating model to go and look out of sample. Can I forecast volatility? And of course the answer is yes. In terms of notation, today is denoted with n, so we have used historical data from time 1 to time n. So n is the moment where I have my last observation in the sample. And now I want to go out of sample into the future, and I want to go small t periods out of in the future. So my question is, well, if I want to know what my expected variance is at time n plus t, so that's the expected value of sigma n plus t square, then I use the gauge representation as I had it before with the variance targeting, and I simply change the index with the u and with the sigma, because it then says, well, you have to take the u n plus t minus 1 square on the right hand side, and you take the sigma n plus t minus 1 square as well. And there's the VLs, which are the historical average variance. So this is simply the gauge model as we also use it for estimation, but we change the indices. And there is another important element that change, because we look in the future, the values are not known, and the only thing that we can do then is we can take expected values. So the E operator every time then says expected value. So it's already on the left hand side. What's the expected volatility at time n plus t? Well, I need the expected innovation at time n plus t minus 1 square, and I need the expected variance at n plus t minus 1 square as well. There is an important property that you have to know, and that is if I take the expected value of u n plus t minus 1 square, that's the same as the variance at n plus t minus 1. So if I do that, if I know that and I substitute that in the upper equation, so what I do get is I get the expected value of the volatility, the variance at time n plus t, is the long-term unconditional variance, plus, and now I can add up the alpha plus the beta, times the expected value of sigma n plus t minus 1 square minus VL, because the two terms on the right hand side, just after the alpha and the beta, they are identical, so I could add it up. So this is an iteration between sigma n plus t square minus VL and sigma n plus t minus 1 square minus VL. I simply bring the VL to the left term. And if I reiterate this iteration, I could in the end find a relationship between the expected variance at time n plus t and the expected variance at time n. And the relationship is simply that you have the long-term unconditional variance, the VL, plus alpha plus beta to the power t times the expected value of sigma n square minus VL. A reiteration of the previous formula. So why do we do this? We do this because the expected value of sigma n square actually is sigma n square, because this is the variance, that the last variance that we could calculate in sample of the gauge model. So that model, that value is still fitted using the historical data. So we actually observe between parentheses, we can calculate it at time n, because in time n we have the last observed value. So I could then get rid of the expectation operator on the right hand side. So I have then that the expected value of my variance in the future at time n plus t is equal to the unconditional long-term variance VL plus alpha plus beta to the power t times the last observed variance in sample, sigma n square, minus VL. So really, everything is known now. So the only thing that is unknown is the time t. That's the moment where I want to determine the value. This equation very often is then rephrased. So the expected value of the daily variance at time n plus t square, so that's t periods out of sample, is denoted with the capital V and then between parentheses t. It's equal to the unconditional long-term variance, the VL, plus the exponent to the power minus a times t, times the variance at time 0, the daily variance at time 0, that's the last one known, that's the sigma n square, minus the unconditional long-term variance, the VL, and then in rewriting this, the a is simply the logarithm of 1 over alpha plus beta. So what this equation does, the way that we have defined it, is that it says, well, once I've estimated the gauge model in sample, then I could use the alpha and the beta that I've estimated, plus the unconditional long-term variance, the VL, which is simply the variance of all the historical data, plus the sigma n square, which is the last daily variance that I've observed in sample as an outcome of my gauge model. These elements, so if I put them in a formula, are exactly the elements that I need to see how the daily variance moves over time if I'm going to forecast the variance in the future. So it's a very convenient and easy formula that you arrive at. So you simply need these elements that all come from historical data. You plug in the t, which is also then in days, to have an assessment of the expected future daily variance. Well, one of the usages of future variances is when I'm going to look to pricing of options. If I look to price of options, then an element, an input to the Black-Scholes formula is the volatility which applies to the particular time period that, that holds. So if that volatility is not constant but is changing over time, and that's exactly the case for the gauge 1 model and the exponentially weighted moving average model, then I could make good use of the fact that I know that the volatility is not constant, but instead it's time varying. So what do I need exactly in the option pricing formula? I need an average of the volatility over the time period from today until maturity of the option. And I don't need it expressed in daily terms, but I need to annualize it. So first of all, so this variance that I'm then going to use, and please note that different frequencies now become important. The variance that I use, the volatility that I use as input to the Black-Scholes formula is denoted with sigma between parentheses capital T. So that's the Black-Scholes formula. That's the volatility that goes into that formula. Well, here to facilitate notation, I take the square of that, so that's the power 2. And I need to do two things. I need to multiply with 252 to go from daily to annualized, because the variance needs to be annualized. If I need to annualize standard deviations, I multiply with the square root of 252. But given that I look to variances, I multiply with 252. That's the first thing. And the second thing that I need to do is I need to take the average of all the future volatilities within the term of the option. And so here, to take the average, I use the assumption that this variance is continuously developing. So then it's 1 over t times the integral from 0 to time capital T of the daily forecasted variances that I'm looking at. So that's then instead of taking a sum in continuous environment, you could take the integral, which is then say the proxy for the sum. So the average 1 over t times the integral of Vt dt, Vt being the future forecast variance on a daily basis. So if we then substitute the expression that we have from the previous slide, the VL plus exponent minus AT V0 minus VL dt, and I solve for that integral, then I get the 252 because I need to annualize, because the Gauge model was on a daily basis, I need to annualize 252. I have the VL, and when I solve for the integral, I have 1 minus the exponent minus AT over AT times the daily forecasted variance at time 0, which is the last observed variance in the Gauge model, minus long-term unconditional volatility, also on a daily basis. So for the Black and Scholes formula, what I need to plug in is that volatility, which means that I need to take the square root of that expression. And then it's very simple, just only not forgetting that the time of the option, the time to maturity of the option here is expressed in days, so I need to take care of that when I'm doing the option prices. I need to not forget that it's not in terms of years. There's another feature that will come in handy afterwards, is that if I look to the current annualized volatility, so that means that if I would look to an option which has a very small time to maturity, time 0 to maturity, I fill in the 0 and I use L'Hopital to look to what these values then actually arrive at. I see that the sigma at time 0, so which is the sigma that flows into the Black and Scholes formula, the instantaneous sigma, is equal to the square root of 252 times sigma n there. So there is also this relationship that I need a little bit later. So I'm going to do option pricing, and the question is, well, what volatility to use? So the Black and Scholes formula assumes that volatility is a constant. With the Gauge 1-1 model, we know that volatility is not constant, but it's changing over time. We use the Gauge 1-1 model to afterwards forecast the future daily volatilities, and then we take the average of that. So we already did that, and then we annualize it. And then there was this formula that appeared. And then if I'm going to plug in the parameter estimates that I have from the Gauge 1-1 model, then the relevant table is the table at the bottom middle, bottom right. So the left column says the numbers of days until maturity of the options. So that's 1 day, 2 day, 3 days, and then 30 days, 50 days, 100 days, 500 days. And then the other column, the sigma t, says, well, what is then the relevant volatility that you need to use in the Black and Scholes formula to determine the price? And then you see if the remaining time to maturity is low, it's 1 day, then the volatility that should be plugged in is 12.2%. But as we move further in time, and for example at 30 days it's 11.55%, and at 500 days it's 10.64%. So we do see that with a different term for the option, the volatility that you should apply is not a constant volatility, but it's a volatility which is decreasing in this case with time. And a different volatility as input to the Black and Scholes formula has a relevant impact on the price that in the end is assessed. So it's an important element to take into account. So we refer to this table as the term structure of volatilities. With a different term for the option, there's a different volatility that applies. In this case, the relationship is inverted, So for short-term options, we should use higher volatilities, and for long-term options, we should use lower volatilities. Second question that you could ask as well, I'm not only concerned when I look to options with pricing them, but I'm also concerned with the risk that is associated with the options. And given that we look to volatility right now, we may wonder, well, what is the implication for the option VIGA? So what risk measure would you like to use? Well, recall again that formula that we have derived for the sigma t, for the volatility that should move into the Black-Scholes formula. So if I take the square on the left and on the right side, then I get rid of the square root sign. And what I do on top is the V0, and that's 2 slides ago I showed that. The V0 is because it's the daily volatility in sample, it's also the implied volatility, or the volatility that should be used in the Black-Scholes formula. So the sigma 0 square, but given that sigma 0 square is an annualized formula, I divide it by 252 to make that exactly equal to the V0. And so the V0 is sigma 0 square divided by 252. 2 slides ago I showed you that also as a derivation. But that's the second thing that changed if I go from the upper formula to the second formula. And the reason why I do this is the following. So what I want to understand is that when I look to VIGA, I always look to instantaneous changes in the volatility. So I look to changes in the volatility at the very short end of the term structure volatility. So I'm looking to changes in sigma 0. And what I want to know is, well, if on the short end of my term structure volatility something changes, so the instantaneous volatility changes, that's the volatility that normally goes into the Black-Scholes formula. What happens with the volatility of longer term options, the sigma t? So now, so that's why I did the substitution. Now I have a relationship between the volatility for longer term options with the term t, capital T, that's on the left hand side, and on the right hand side, the volatility that I use when I need to price an instantaneous option, the sigma 0 square. So to understand the relationship between the two when things change, I take a partial derivative on the left hand side and I do the same thing on the right hand side. So that means that if I take sigma t square, if I want to know how that changes, I need to take the first derivative, which is 2 times sigma t times d sigma t. And on the right hand side, I'm going to do a change in the sigma 0, which means that the values that will remain are the 252 times the 1 minus the exponent minus at over at times 2 times sigma 0 d sigma 0 divided by 252. And then if I rearrange, then so all the constants they disappear. And if I rearrange, then what I get is, so I can cancel the 2's on left and right hand side. I can cancel the 252's in the numerator and the denominator. Then I get a relationship of how the change in the long-term volatility, so the d sigma t, so the volatility that I use to price long-term options, how that relates to a change in the instantaneous volatility, the d sigma 0. So what it says is the relationship between the two is that I need to know the volatility at time 0, and I need to know the volatility at time capital T, that applies for that longer period, and I need to pre-multiply that with 1 minus the exponent minus at divided by at. And the a is the logarithm of 1 over alpha and beta. So perhaps a complicated formula, but what happens is that simply it says, well, if there's a change at the short term of the yield curve, what's then the implied change on the longer term of the yield curve? So I'm not assuming a parallel shift anymore, but I assume that there will be a shock in the instantaneous volatility, so a shock in sigma 0, and I want to know, well, what are then the shocks in all the other volatilities. And then there is on the right hand side again a table with the first column the time to maturity of the options and then measured in days. There is the original volatility, which we have calculated already when we were looking to the prices of the options. And we assume that there is a 100 basis points or 1% change in the instantaneous rate. So that's where T, capital T, is equal to 0. We see that the T delta sigma T, so it's delta sigma 0, is equal to 1%. And then we use that formula to see, well, what's then actually the change in the 1-day rate, in the 2-day rate, in the 3-day rate, and so on. And then we see, for example, for 30-day options, we see that if the volatility, the instantaneous volatility changes with 1%, then for 30 days options, the volatility that I would need to use if I want to price a 30-day option only changes with 0.61%. And even further, if I would go to a 100-day option or a 500-day option, you see that a 1% change in the instantaneous volatility only, say, has an effect of a change of 0.27% in the 100-day option or 0.06% in the 500-day options. So there may be a large effect then for options with shorter terms, but the effect is much smaller for options with lower terms. So the new volatility is much lower, much less changing for longer term options than for short term options. So that's an important effect of the volatility risk. So the VIGA risk, we say then, which is the volatility risk, has a far lower impact for long-term options than for short-term options. And that's due to the fact that volatility after a shock is mean reverting again back to the long-term unconditional variance, standard deviation. So it's an effect that is important to understand, because if I would assume parallel shifts in the entire yield curve, then I would overestimate the risk present in long-term options, because this equation says, well, actually the risk, the VIGA risk is lower. So now we have come to the last part of today's lectures. Today's lecture, which is concerned with the power law. As you recalled from the beginning, where we looked to summary statistics of the S&P 500 returns, we saw that the empirical returns and the empirical summary statistics that go with that, that they implied that the tails of the distribution function, so the possibility of extreme events, are much larger than implied by the normal distribution function. So if you are really concerned with extreme risks, then that's an inconvenient thing to simply use the normal distribution function. Well, as a simple alternative, if you're only interested in extreme returns, you could use what is called the power law. And what the power law says is, well, if you look to any type of distribution function with fatter tails, so we will a bit later in the course, we will look to Pareto distribution, for example. If you look to the shape of probability distribution functions very far in the tail, then most of these tails, they have a very similar shape. So in this particular case, if V denotes a random variable, and I look very far in the tail, so I look to X values which are very high, which are very extreme already, then that means that I'm looking to what is the shape, what is the probability very far in the tail. Then you could model that with a constant capital K, then that extreme value X, and to the power minus alpha. So there is this convenient property that the shape of the distribution function is of this form. You could take logarithms, natural logarithms on the left-hand side and the right-hand side, which then basically says, well, if I take the logarithm of this probability that a random variable is larger than a value x, where x is extreme, then that's equal to the logarithm of this constant k minus alpha times the logarithm of x. And in order to apply a formula like this, we first need to find values for k and for alpha. And then once you have that, then you can of course fill in different values for x and then determine what the probabilities are. So important, this value x is an extreme value. I need to be in the tail. So later on we need to wonder, well, when are we in the tail? So for what values does it apply? And of course, once you have the values for k and alpha, it becomes very handy if I need to determine extreme value probabilities. So I have some banks that have, for example, a AAA rating. They need to look to events that could occur once every 10,000 years. Well, you don't have sufficient historical observations to see what occurred once every 10,000 years. So instead, what you could do is you could apply the power law and then simply look for the data that you have, what the tail is like, and then afterwards do an extrapolation using this power law to go to these very low extreme probabilities. So this formula also comes in very handy to look to probabilities for occurrences where you don't have actual historical data at your disposal. An important element as well, if you want to apply the power law for risk management purposes, then there's one type of tail that you particularly are interested in, and that's the left tail of the distribution function, because that is the part of the distribution function that is concerned with losses, and the right side of a return distribution is concerned with gains, with profit. So that's also important, but it's not what the focus is at. So the first thing that you need to do once you're going to look to the left tail, because the representation of the power law is to look to a random variable which looks to values greater than x, is that in fact you need to represent this left tail by a right tail distribution function. And there's a very easy way to do that, and that's simply to multiply all your returns with -1, because then the most extreme return, which is the highest negative return, will then become the most positive loss that you have. So we move from returns to losses, and we're going to look to the most extreme losses. And then the power law, given that it focuses on the right tail always, is then correct. So the V here has as an interpretation a loss. Where does the tail start? Well, that's an obvious question. Well, if I need to estimate the alpha and the k, I need to do that based on historical data. But given that the power law applies for the tail of the distribution function, I need to look where the tail starts. And a way to do it, given that we saw on the previous slide, if you look to the formula in the middle, once I've taken logarithms, it says that the logarithm of the probability that v is greater than x, in fact, is linear, has a linear relationship with the logarithm of x. So what I simply can do is I can then look to a plot of these two variables, the logarithm of the probability that the v is greater than x and logarithm of x. And in the plot where I see that the variables have a linear relationship, that's where I say that my tail starts. And from there on, I will use the data to estimate the k and the alpha. So, for illustration purposes, I use monthly returns from the S&P 500 index from 1978 to 2019. I've multiplied the returns, these monthly returns, with -1, so I look to losses. And then I take the logarithm of these losses, and I take the logarithm of the probability that there is an excess of this loss. And the way that these probabilities are determined is simply by looking to how many cases out of the total number of cases have occurred. So that's a frequency approximation to determine the probability. And then you get a graph like this. On the x-axis is the logarithm of x, and on the y-axis is the logarithm of this probability. And then I am in particular interested in the case where there's a heavy heavy decrease in the graph, because there at one moment in time I see that there is this linear relationship, and the y-axis has disappeared here. But what you will see from the data is that where the logarithm of x is greater than -3, so -3, -2, -1, etc., that's where there's the heavy decay, and this heavy decay more or less looks linear. So we will say, well, in order to determine where the tail starts, where there is a linear relationship between the logarithm of x and the logarithm of the probability that the loss is bigger than x, is at -3. So here you see a snapshot of the data. So the most extreme return was -24.5%. I multiply that with -1 to get a loss of 24.5%. And as a frequency, there is no observation in excess of this value. So the probability that there is an observation in my data bigger than 24.5% loss is 0. Then the next extreme return is -18%, multiplied with -1 to get to the right tail. That's a loss of 18.6%. There's only one observation that's more extreme than that, one bigger loss of 24.5%. So the frequency is then one observation over the total number of observations in my sample, which gives then a probability of 0.55%, and so on. Then once I have the values, then I can take the logarithms, and I can take the logarithms of the probabilities, which is the logarithm of the v column and the logarithm of the probability column. And it's then these observations, and I've not put it all of them because I should have gone a little bit further until the logarithm of x is -3, but it didn't fit on the slide. But these are then the two columns, the logarithm of x and the logarithm of the probability that v is greater than x. These are the two columns that I'm going to use to estimate the alpha and the k. And that relationship between the logarithm of x and the logarithm of the probability is a linear relationship if ln k is a constant and minus alpha is a slope coefficient. So I'm going to use the regression function in Excel, and the regression output is shown here. First of all, I see that the adjusted R square is 0.95%. So an R square of that amount says that there is to a large extent a linear relationship between the logarithm of x and the logarithm of that excess probability. So that says indeed I'm far enough in the tail, because, well, we assume that very far in the tail there should be that linear relationship. So then what I can do next, I can use the intercept and the x variable, which are the coefficients at the bottom of -9.87 and -2.91. I can use them as estimates for the logarithm of k and minus the alpha. So that's what is on the bottom, on the top right. And then if I take the exponent of the logarithm of k value, well, I get to a very small value, which, with the precision of 3 decimals is 0.000, but there are, say, numbers still further to the, with further decimals, and the alpha is 2.912. So I have used historical data. For this historical data, I have determined where the tail starts, and I've looked at historical returns. I've sorted them, and I've seen, well, what are the most negative returns. I've transformed them in losses by multiplying with -1. Then I have determined, so where does the tail start, because in the tail I believe that the power law applies, and that there is this linear relationship between the logarithm of x and the logarithm of the probability. I've estimated that relationship, which gives me a k and an alpha, and now I can apply that relationship. So that's what I did over here. So I said, well, let's look to losses of 10%, 20%, 30%, 40%, 50%, which is equivalent to returns which are larger than minus 10%, returns larger than minus 20%, and so on. And then what does the power law tell me in terms of probability? So there's a 4.2% probability that the loss in terms of returns is bigger than 10%. There's an 0.56% probability that the loss is bigger than 20%, and so on. So even for a loss of 50%, this as a monthly return, so the probability that the return is more extreme than minus 50%, there's still a probability of 4 basis points. So what the power law allows you to do, it allows you to calculate probabilities even there where you don't have any observations anymore in your sample. So it's a very nice feature. And that concludes the lecture for today. Thank you for your attention.